this is Math 139, Section 3.2. We're going to begin looking at exponential functions. And an exponential function has a particular form, a times b to the x power. Okay? So just like you know, linear functions are y equals mx plus b, or quadratic functions are y equals ax squared plus bx plus c. This is just another new form for you. F of x or y equals a b to the x. We're going to graph a couple of fairly simple exponential functions by hand, just to get a feel for them, and then we'll go ahead and, let the calculator help us eventually. But these first couple I'd like to do by hand. My function f of x here is 2 to the x power. Notice I've let the a be 1, and my b, called my base, is 2. If x is negative 3, and I plug that in, I would have 2 to the negative third, or 1 over 2 cubed, which would be 1/8. Plugging a negative 2 in for the x would give me 1 over 2 squared, or 1/4. And plugging a negative 1 in for the x gives me 1 over 2 to the first, which is just 1/2. The rest of them are a little bit easier. 2 to the 0, that's just going to be 1. 2 to the first would be 2. 2 to the second, that's 4. And 2 to the third is 8. All right, I'm going to graph these. I'll have to do a little estimating with the fractions, but that's okay. Negative third, y is 1/8. Negative 2, y is 1/4. Negative 1, y is 1/2. I've got 0, 1. 1, 2. And 3, 8. Excuse me, 2, 4, and 3, 8. All right, clearly this is not a linear function, nor does it look like a parabola. This seems like it's just going to keep on getting to be smaller and smaller fractions. It's not going to come back up. So this does have a graph with a shape of its own. This side goes up faster and faster. And the other side is going to just get very, very small, very, very close to the x-axis. It never actually goes negative. Excuse me. I'm going to show that the best I can by hand, just by kind of drawing a line that comes really close to that x-axis. I know technically it gets closer and closer, but I don't want to touch the axis, because that function will never equal 0, no matter what the negative exponent is. You'll always have some positive denominator. All right. This is called an exponential growth function. And this curve typifies exponential growth. It gets big, and it gets big quite fast as we increase the value of our x. Let's try this other one. This time, again, my a value is 1, but I'm using a b, a base of 1/2, and y is equal to 1/2 to the x power. So if I start by plugging the negative 3 in for x, that would actually be 1 to the negative third over 2 to the negative third. And since they are negative exponents, I'm going to bring them across the fraction bar to make them positive. 2 cubed over 1 cubed. That'd be 8 over 1, or 8. Same idea with the exponent of negative 2. It's really 1 to the negative 2 over 2 to the negative 2, which if I crisscross the fraction bar here, that'd be 2 squared over 1 squared, which would be 4. One half to the negative first, exactly the same idea. And when I move my factors across the fraction bar to make the exponents positive, whoops, sorry, that was a negative first there. I'll have 2 to the positive 1 over 1 to the first, or just 2. All right, when I put 0 in for the x, 1/2 to the 0, anything to the 0 is just 1. When the exponent is 1, 1/2 to the first is 1/2. When I plug in 2 for my exponent, I'd have 1 squared over 2 squared. That would be 1/4. And finally, when I plug in 3 for my exponent, sorry, let me try that again. 1/2 to the 3rd power, I'd have 1 cubed over 2 cubed, or 1/8. Once again, we're going to go ahead and just plot those points. So -3/8, -2/4, -1/2, 0/1, and again, I'll have to do a little bit of estimating here with my fractions, but that's okay. We see that same kind of thing happening. Those fractions are getting smaller and smaller, closer to 0, but they'll never be negative, right? All of those values are always going to have a positive 2 to some power on the bottom. So if I connect my points with a sort of smooth curve here, once again, I'm going to clearly show that these are small but staying above the x-axis. I have almost the reverse of the curve I drew above, right? And this is called exponential decay. The values of y get smaller and smaller as we increase the x. All right, on the next page, we've got just some sort of summaries of what we're seeing here. So I'm going to leave our graph up so we can do this. Assuming that both a and b are positive values for right now, then the function f of x is equal to a b to the x has the following properties. Anytime the base b is larger than 1, like it was here, we are going to always end up with exponential growth. And in any exponential growth function, notice our graph is increasing as we read it from left to right. Where the graph gets very close to the x-axis, we call that a horizontal asymptote. The word asymptote is really just the mathematical word for a line that a graph stays very close to, but does not touch. In this case, it's the negative side of the x-axis that is our horizontal asymptote. If I go back and remind us what our other graph looked like, the exponential decay graph, notice that in the second graph, the base was smaller than 1. In fact, anytime our base is between 0 and 1, we have exponential decay. And in this case, our graph is decreasing as we go from left to right. Our horizontal asymptote, where the graph gets really close but doesn't touch, is now on the positive side of the x-axis. All right, let's talk a little bit more about these. The y-intercept of the function f of x equals b to the x is actually always the same. Remember that for a y-intercept, we always want to plug in x equals 0. So if I plugged in 0 for x, I'm going to get b to the 0 power, and of course that's going to be 1. So the y-intercept of those functions is always 1. Notice on my graphs, there was that y-intercept of 1. And there again, that y-intercept of 1. More generally, if my multiplier, my a value, is not always going to be 1 like it was so far, I could have any a value. So once again, if I want the y-intercept, I'm just going to put 0 in for the x value. I'd have a times b to the 0, or a times 1, which is just going to give me a. So the a value of an exponential function is going to end up being its y-intercept every time. That's going to help us a little later on when we start graphing. All right, let's think about domain and range. I'm going to go back to our graphs one more time. Notice that we could put any x value into this function, right? I could plug in any x and I could calculate the y. This graph exists for every possible x value. It gets really big, so some of these x values over here might be really giant. I may not be able to see them, but certainly the x value is possible. The same thing is true for the exponential decay function. So I'm going to say the domain of an exponential function is all real numbers, or negative infinity to infinity. What about the range? Well, all of my y values in this graph are definitely greater than 0. And in fact, because the graph never touches the x-axis, y never equals 0. So it's strictly y values bigger than 0. And once again, that same idea applies with the exponential decay. So when I list my range, I'm going to go from 0 to infinity, but I don't want to include the 0. The graph never touches 0, so I'll use a parenthesis there. All right, we will now be able to graph exponential functions using the same ideas with the transformations of graphs, left, right, up, down, upside down, that we've seen a couple of times already in this course. When we do our transformations, the things that I would like you to really pay attention to and get in the right places are be sure to apply your shifts to the y-intercept and the horizontal asymptote. If you get those two things in the right place, then simply sketching exponential growth or exponential decay from there will be just fine. So here are a few examples. 2 to the x we already graphed. We know what that looks like. It's exponential growth. And I'm just going to remind myself that's like this. As far as transformations, this has been moved down 3. That means when I take my horizontal asymptote, which is usually on the x-axis, I'm going to move that down 3 units. So my new horizontal asymptote is going to be down here. It's typical accepted mathematical notation to draw asymptotes in as dotted lines. They're not actually part of the graph, but they're recognized as guidelines, asymptotes. All right, in addition to, so that my horizontal asymptote then is down here at y equals -3. My y-intercept was originally at 1. I'm going to also move that down 1, 2, 3. So my new y-intercept is down here at y equal -2. From there, I'm simply going to sketch an exponential growth curve. And I'm not going to be too picky as far as exactly what your y values are. I really just want to see that y-intercept, that horizontal asymptote, and that you understand the basic shape of an exponential growth curve. My domain is still negative infinity to infinity. But now that we've shifted down 3, notice that the y values are all bigger than 3. From 3 to infinity. Excuse me, negative 3 to infinity. We shifted down 3, right? I did use a parenthesis on the negative 3. The graph never actually touches that asymptote. All right, let's try another one. This time, notice my base is 1/2. So this is going to be exponential decay. And again, I'm just going to remind myself of what that looks like. As far as transformations, this graph has been moved to the right 1. All right. The horizontal asymptote doesn't change with a left or right shift. If the x-axis was the original horizontal asymptote, moving the x-axis left or right doesn't change that. So my horizontal asymptote is still going to be the x-axis, or y equals 0. This time, I've got an a value that's not 1. Notice a equals 3. That means that originally the y-intercept would have been at 3. But I am moving or shifting to the right 1. So I'll shift that over here. Other than that, I'm simply going to sketch in an exponential decay curve. I know I need to go through that point, and I need to approach that horizontal asymptote. And there we go. Domain remains at negative infinity to infinity. And the range on this one, all the y's are bigger than 0. So from 0 to infinity. All right, one more. Negative 1/2 times 3 to the x plus 5. The base is 3, so this is exponential growth. Again, I'm just going to remind myself, exponential growth looks like that. And as far as transformations, I have a negative multiplier. So it's going to be upside down, or reflected across the x-axis. It's also shifted up 5. So I'm going to start with my horizontal asymptote. Starting from the x-axis, it's shifted up 5. So there's my new horizontal asymptote at y equal 5. The original a value was negative 1/2. But I have to move that up 5 as well. So from negative 1/2, I'm going to go up 1, 2, 3, 4, 5 to right there. Now imagine this exponential growth function tipped upside down. And we can see that I'm going to approach the horizontal asymptote over here. And this time it grows in a downward direction rather than an upward direction, if you want to think of it that way. Doesn't change the domain, negative infinity to infinity. But my y values go all the way down to negative infinity up to 5. All right, that concludes part A of the section.